Hello, my name is Luke, and welcome to this reinforcement learning series. This is the fourth video in this series. In the first two videos, we covered reinforcement learning basics. In the third video, we covered deep reinforcement learning. So if you're unfamiliar with reinforcement learning or deep reinforcement learning, I suggest you have a look at those videos first. At the end of the deep reinforcement learning video, I said that if there was any interest on some more advanced algorithms, we can do a video on that, and there was. So in this video, we're covering a more advanced policy gradient algorithm called Proximal Policy Optimization, or PPO. That's quite a well-known and widely used for sort of real-world applications when reinforcement learning is needed. So we're going to, in this video, look at background around PPO, and we're going to implement PPO on a more complicated environment. So there's a bit of a step up in the actual implementation compared to the last video. We're going to be training on the ProcGen environments, the procedurally generated environments that I sort of touched on at the end of the last video. And then we're going to be training a deep residual convolutional neural network to play the games using the actual frames of the video. So quite a step up in terms of complexity. As per usual, we're going to look through a lot of the fundamentals and the concepts first, so that we can understand the implementation a bit better. Okay, so the motivation, what is PPO doing and why is it better? So at the end of the previous video, we looked at our policy gradient methods, so using policy-based reinforcement learning with neural networks. First, we showed how we could use value-based methods like Q-learning with reinforcement learning, and showed how, also with deep learning, and showed how we can successfully implement a Q or a deep Q learning algorithm to simulate, play some sort of simulated game. And we sort of showed how we can use some of the similar ideas to get our policy-based methods also working with neural networks, but there was some issues there. Training was sort of inefficient and it was a bit unstable. So go over that again. So problems with our vanilla actor-critic methods, so our policy gradient or actor-critic methods, where we have a policy and which is our actor, and our critic, which is our value function. So we know there's issues with our value estimates, which we use for calculating our advantage. If we're using TD-based learning for our value, that sort of can introduce some bias. If we're using the returns calculator, that can introduce some noise. And this bias and noise can lead to slow convergence, or we might not converge at all. We also talked about how we can't do many update steps between our rollouts. Right, we could overfit our value function, and we might accidentally change our action probabilities too much and actually reduce the performance of our agent. We talked about how our value function is our value function for a given policy. Right, we looked at in the very first video in this series how tied the value function is to a particular policy. And in our policy gradients, when we looked at deep learning, we talked about how, as a result, we can't use values or even rollouts from older agents to update when we do our gradient descent steps to train our neural networks. We can't use a value function from an old agent to train our new agent. What that means is that we have to throw out our sort of stale rollouts and can only use the ones that we've just collected, which means we can't do too many gradient descent steps. And as we also touched on, even if we had a lot of data in our trajectories to actually update our model, by updating our model too much, we can actually make performance even worse by changing the action probabilities too much. So this is what we're going to try and fix today with PPO and some of the prior works as well. So remember our basic actor critic. Our advantage, we said, is just the difference between our returns and our value function. So how much better did we do in this trajectory for our returns compared to the average? And then we do our policy gradients update, multiplying the advantage by the log probabilities. If the advantage is positive, we want to increase the probability, so we're maximizing this. If it's negative, we want to reduce the probability, reduce this. Again, how many steps of gradient descent can we do with a given advantage, right? So we want to increase the probability, but how much? We want to decrease the probability, but how much? If we increase or decrease it too much, we can actually make the performance worse, because again, all the advantage says is increase it or decrease it, we think, right? It's an approximation of the actual true advantage, so it's a bit noisy. So we don't want to trust it too much. So what can we do? Well, we're going to actually cover quite a few things in this video. This is actually over 3 papers, all authored, or all first authored by the same person, John Schultman, for his PhD, I think. So TRPO is what we're going to look at first, or Trust Region Policy Optimization, and this sort of establishes the concepts that PPO later approximates, right? So TRPO is all about how we can limit how much we update our policy during training. So it introduces this idea of a trust region. So it's saying that we trust our old policy to some degree, and when we're updating our new policy, or when we're updating our policy to improve it, we don't want it to stray too far away from our old policy. So then generalized advantage estimate, or GAE, is a way of directly calculating the advantage to use in our actor-critic methods without having to calculate sort of the returns beforehand. It's noisy, and it's also a way of sort of combining TD and Monte Carlo learning when calculating the advantage. And then finally, we'll look at proximal policy optimization, how we can take the ideas of TRPO and create an easy to implement approximation that works quite well. Okay. So again, just to go over the training procedure for our deep reinforcement learning agents and to clarify some of the terms I'm going to be using. So we have our agent acting in the environment, and we perform our rollouts or our trajectories in that environment to collect data. I'm calling this agent here the old policy to contrast it with the new policy. So once we collect our data, we then use that collected data to train or update our policy to get our new policy. Right, and that training procedure could be iterative, where we can do multiple steps of mini-batched gradient descent for our neural networks. And every single step we take during training, every single gradient descent step we take, we're changing the parameters of our model, and we're getting, therefore, a new policy. The new policy is the policy that we currently have at this step in training, whereas old policy specifically is the policy that we used to collect the data that we're using during training. Right? Then we get the new policy, then we put that in our environment, and it becomes the old policy for the next loop. Okay, on to TRPO, or Trust Region Policy Optimization. So there is quite a bit of work between where we left off with actor-critic methods and getting even into TRPO, later PPO. There's a lot of theoretical and conceptual works that show how theoretically or conceptually you can ensure monotonic improvement of your policy over time. TRPO builds off of a conservative policy iteration that we'll see. We'll talk a little bit about later on, but the main contribution of TRPO again is to say, okay, well, we need to maximize this objective, we need to increase the probabilities, but none of this theoretical standing actually says how far can we take it. That third point here, for parameterized policies like our deep neural networks, we need to calculate a gradient, we need to calculate the derivative. The derivative sort of tells us the direction to go, but we don't know how big a step we can take. And reinforcement learning can be quite unstable, and if we take too big a step, we can actually end up collapsing our policy, as we've talked about before. Okay. So as I mentioned, TRPO introduces this concept of a trust region, this conceptual region around our old policy that we say is sort of safe, and we want to limit how far our new policy can stray from our old policy. And TRPO does this mainly by defining this constraint that must be satisfied while we're updating or training our new policy. So this first part here is actually the conservative policy iteration update step. You can see it's pretty similar to what we've seen before with our actor critic policy gradients update step. Here, instead of taking the log of the probability of an action given a state, we're just taking the probability for our policy. So this is just the probability of taking this action in this given state, and we're dividing it by the probability of taking that action in the same state given the old policy, and multiplying that by the advantage, and we're maximizing this. Again, if the advantage is positive, we're backpropagating through the new policy. So we're increasing the probability or decreasing if the advantage is negative. There is quite a lot of theory behind this and concepts behind this, but I'm not going to cover that for the sake of making a short video that's easy to understand. But one thing I will note is that here, dividing by the old policy here, we do that not because of the fact that it's the old policy in any strict reason. We divide it because this is the policy that we used, or this is the method that we used to collect the data. And in the actual theoretical framework or the concepts behind this, we can sort of use any policy or any methodology to sample from the environment, perform our rollouts, our trajectories during the rollout or collection period before training. And this here is the probability given that procedure, whatever it is, that we took this action given this state. So if you've delved into the research at all, or even just done some reading on it, you might have heard that there's actually quite a different number of ways that during these rollouts that we've kind of kept simple, you can make them quite complicated. Have branching rollouts that from the same state, you actually sample multiple different trajectories into the future and do a whole bunch of crazy stuff. Here, I just wanted to point out that this is actually just a probability given whatever procedure you use during the data collection procedure. However, if you used the old policy during the data collection procedure and just used it normally, that's what you'd get. You'd get the old policy on the bottom here. I just wanted to contrast that with using the old policy here when defining this constraint. This is always the old policy, irregardless of what you used to sample during the rollout procedure. So this is what we're trying to maximize. That's our objective. And this constraint here is basically saying that we want to make sure that the KL divergence, if you're unfamiliar with KL divergence, it's enough for now to know that it's just a measure of the difference between probability distributions. So here it's just saying that the probability distribution over the actions for a given state between the old and new policy needs to be less than some amount. And that's just going to be a hyperparameter that we choose. Note here, this is not a loss. This is a constraint. And this is where it gets a bit tricky with TRPO. Because what we're saying is that you can take steps of gradient descent to maximize this, as long as you can be sure that this constraint is satisfied. So how do we make sure this constraint is satisfied? Well, there's a number of different ways you can do it. There's a lot of different ways you could do it. You could just take a very, very, very small steps of gradient descent for a very small learning rate to maximize this objective, and just always be checking if this is true. And as soon as it is not true, or if it gets close to not being true, you stop. So for the same inputs of our neural network, we're doing tiny little steps of gradient descent, always just checking that this is satisfied, and then stopping when it's not, or stopping before it's not true. And TRPO, they do a bit more complicated. What you can do instead is actually see how this constraint is changed for different sizes of steps, or different step sizes, and then pick a step size to maximize this, knowing that this will be satisfied. However, that search procedure is actually quite complicated, and so even me just describing it here, hopefully you can get an idea of how complicated it is, because you introduce this constraint, not a loss that you can backpropagate through. It's this constraint that must be satisfied. So whereas it's a good idea, and it does in practice help a lot make sure that we don't increase or decrease the probabilities of our policy too much, and making sure that our new policy stays sort of within this trust region of our old policy, it is quite difficult to actually implement in practice, especially if we're using complicated neural networks. So keep that in mind for now, and we're going to move on to our general advantage estimates. This is from the paper High Dimensional Continuous Control Using Generalized Advantage Estimation, also by John Schulten. So as I already touched on, GAE creates an estimate of the advantage that is less noisy and less biased by combining the two methods you would use to calculate the advantage, or specifically calculate the returns. Remember, there was two ways we could calculate the returns directly, or we could approximate them using temporal difference or using the actual value function. So this is the equation, and we'll sort of unpack this now. This is our GAE. You can see it's a sum, or a discounted sum of these terms here. And each of these terms here are just that, we call it TD residual, but this is just the sort of TD update we would do, again, going back to the first video in the series. And we know from that as well that this first part here, the reward plus gamma, our discount factor for our reward, times the value of the next state, right? This is an approximation for our returns, right? So we're using the value of the next state as an approximation for the returns in the next state, and we're approximating the returns in the current state by the reward we got plus gamma times that value. So this is our approximation of the returns. Subtract the value, that's our TD update. It's also our advantage calculation, right? This is an approximation of our advantage if we were using the TD approximation of our value function. So you can see that the generalized advantage estimate is kind of like a cumulative discounted sum of the advantage at each of the steps in time into the future, right? So you can kind of see that by changing around the parameter tau. So tau is what we've introduced here and what we're going to use to sort of discount the advantages calculated at each of the steps into the future. So if we set tau to 0, what you can see is that, well, it's going to be 0 here. So this whole term at the front is going to be 0. That's to the power of 0 is going to be 1. And then when L is not 0, then it's not going to be 1. We're going to have 0 to the power of something, which is going to be 0, but it's going to be 1 when L is equal to 0. So we'll get this first term, which is this one, and then plus zeros to infinity. So when tau is 0, we just get that first part here. When tau is 1, it's a bit harder to see. The actual paper does a better job at actually unpacking it if you're interested. But if tau is 1, then this is just gamma discounting these advantages into the future. And what you actually get is you get the value at TS plus 1, and then imagine this term again added here, but instead of TS, it's TS plus 1. So you have a TS plus 1 subtract a TS plus 1 term. In a sense, all the values kind of get cancelled out except for the first one and this discounted sum of the rewards. So what you get when tau is 1 is just the actual calculation of the returns subtract the value. You can see that by changing tau between 0 and 1, you sort of get this combination of the two different ways we can calculate the advantage in TD or using Monte Carlo. In practice, we tend to use a tau pretty close to 1, 0.09 is what we're going to be using. So you can see that, and that comes from the actual paper. They did an ablation, tried a whole bunch of different values of tau, and showed that as you increase tau, performance got better, but actually as it got closer to 1, performance dropped off again. So tau about 0.95. So not having it too biased, but also using the bias or using the approximation or the averaging effect of the value function to sort of smooth out any of the noise a little bit. Don't want too much of it, which is interesting in itself. This paper, the same paper, also talks about introducing a trust region for the value function. So you can think of the value function regression as fitting probability distributions as well, because we need a value function still for calculating the advantage. So we still need the value function. But normally we just do something like this where you could do like I said, the TD update, or you could do the color update to actually calculate the value, but we usually just do something like a mean squared error, an L2 loss. What this paper does in a later on section is say that, well, you can actually pretend that the output of your regression model is a probability distribution, a Gaussian distribution, where your value is the mean of that distribution. You've gone through my PyTorch tutorial series. In the MLP regression one, I kind of talk about this a bit. In any case, you can treat that as probability distributions and say that, well, when I do an update of my value function, I don't want the probability to stray too far away from the probability distribution of my old value function. So in effect, we're creating a trust region around our value function so that we don't update it too far away from the old one, because again, we don't trust our target values of our value that we're trying to regress to that much, because they're noisy, they're biased, and we don't want to overfit to them during the training of the value function. So having this trust region can help with that. I won't go into too much detail because we're not going to be implementing it like this, but we're going to be implementing something a little bit similar. But that brings us on to PPO, finally, Proximal Policy Optimization. So as we saw, TRPO, that trust region, it's a good idea and it can help in practice, but it's computationally expensive and can be hard to implement. So PPO gives us a way of implementing those same ideas, but in a case that's kind of heuristic based rather than actually theory based so much. And it shows that this actual method can perform better than TRPO. And we'll see a bit about why that might be true. And just in brackets here, the paper actually gives a few alternatives to TRPO with the same concepts, but we're going to focus on the one that everyone sort of refers to when they talk about PPO. And it's Proximal Policy Optimization algorithms. So there's a few in there. Okay. So what does PPO do? So PPO takes the idea of this ratio that we use with our conservative policy iteration that TRPO uses. And we assume that this policy on the bottom of this ratio is always going to be the old policy. So that's sampling during the rollouts. We're going to use the old policy for that. So we're going to assume that's true. And we're going to use the fact that this ratio, if that's true, this ratio actually tells us something about how far our new policy has moved from the old policy, right? If this ratio is equal to 1, then they're both the same, or the probabilities are both the same. If the ratio is greater than 1, it means that the probability of taking the action given the new policy is higher. If it's less than 1, the probability is lower compared to the old policy. And what PPO basically does is it forces an explicit constraint when updating our model with gradient descent if this ratio moves outside of some given range, sort of a trust region approximation. So if this ratio basically gets too far away from 1 either side, we're basically not going to update our model. So how does PPO do that? So TRPO, that's a conservative policy iteration objective. So RT theta here, that's not the reward function, that's the ratio between the new and the old policy. And that's the objective for TRPO. And then that has that constraint, which is actually doing the trust region step. But PPO combines it all in one in this approximation. And what we have here is the min between this first term here. This first term here is just the TRPO objective. And then the second objective here is a little bit more interesting. What we have is we have the clipped ratio between these two values. So we take this ratio here and we clip it between these two values. So epsilon here is some value between 0 and 1. We use something like 0.2, I think. So this will be 0.8 and 1.2. We take this ratio, clip it between these two values. So if the ratio is less than 0.8, we clip it to 0.8. If it's greater than 1.2, we clip it to 1.2 and fix it there. If it's in between, then it's whatever it is. Now we take that clipped ratio and we multiply it by the advantage. And then we take the minimum of that. So whichever one of those is smaller, we'll take that. And that is our loss. So what on earth is this doing? So there's sort of two cases where the objective sort of flips. And to see how that happens, look at these graphs here. So in the first case, let's consider that the advantage here is positive. The advantage is positive. So we can see that if the advantage is positive, then we want to increase the probability of the action that we took. So we want to increase the probability. If we increase the probability, then that ratio is going to increase as well. But you can see that we can increase the probability, increase the ratio until we get to the point where the ratio gets out of that range, so 1.2. At that point, we're going to clip and we're effectively not going to increase the probability anymore. So how does that happen? Well, you can see that for now, let's just assume the advantage is 1, positive 1 for both of them. Same advantage. If the ratio is increasing, if the ratio is less than 1.2, then the minimum between the clipped and the unclipped is going to be the ratio until it gets to 0.8. And that sort of region between 0.8 and 1.2, they're going to be exactly the same. And then the only difference will occur when the ratio hits 1.2 or 1 plus epsilon, in which case, which one's going to be smaller? Well, 1 plus epsilon is going to be smaller because the ratio is just going to keep increasing to a value larger than 1.2. So which one's going to be smaller? 1.2, or a value greater than 1.2, it's going to be 1.2. So that is how we get that clipping. The opposite kind of happens when the advantage is negative. So when the advantage is negative, you can kind of think of us taking the max here instead of the min. That helps. So if the ratio is 1 here, so the advantage is negative, we want to decrease the probability. We want to decrease the probability, and the ratio will get smaller if we're decreasing the probability. So we'll go this way until we hit the point where the ratio is 1 take epsilon, 0.8 in our case, and then we clip and we no longer reduce the probability. Again, here, comparing the ratio and the clipped ratio, again, we assume this is just 1, and now we're going to take the max because it's going to be negative. Which one's going to be larger? Well, it's going to be the ratio until we get to 0.8. Then they're going to be the same all the way, right? Which one's going to be larger here? Well, it's going to be 0.8 if the ratio is less than 0.8, and then they're the same afterwards. So that's how this clipping occurs. Okay, so what effect does this have? Or what is this actually saying? There's actually quite a lot going on here. So if during the training or the update steps, right, remember we have our old policy collecting the data, and then we can do a number of update steps. If during that process, the new probability, let's consider the case where the advantage is positive, if the new probability is lower than the old probability, the ratio is going to be less than 0. You can see here we're only clipping one side of it. What this is saying is if the advantage is positive and the ratio is less than 1, we can do as many steps as one we want, or we can do a lot of steps until we get to 1. So until our new policy is similar to our old policy, because we trust our old policy, right? So if the advantage is positive and the probability is decreased, we can say we can push it back a lot. We can push it off really far as long as that's towards the old policy. As soon as we're going past the old policy, we're going to limit how far we can move. So in effect, if those intermediate steps have reduced the probability, which is bad, we can take some big steps or lots of steps until our policy is now the same as it was before, or maybe a bit further on. But again, we're limiting to how far beyond that we can push it. And the same is true with the negative case. If we accidentally increase the probability a lot, well, we can push it really far if it's in the direction of the old policy. But if it's beyond that, we limit how far we can take it, right? So we can correct mistakes, and we still leave room for potential improvement, right? And this is something that TRPO, the trust region, can struggle with if we've done those intermediate steps and we got to our current step to calculate that constraint that we want to put on. Well, if our new policy is already really far out of that trust region, then it can be really difficult to try and work out how to get back in that trust region and progress from there. Right. And we have that constraint. We only maximize that objective if we can remain in that trust region. If we're already out of the trust region, how are we going to get back into it? Well, you can get back into it, but it can be difficult. PPO is basically saying it doesn't really matter if we get into a trust region. There really isn't a trust region, but it's just saying that if the advantage is positive and we're really far away from the old policy and we need to increase the probability, take as big a step as you want, take as many steps as you want. It doesn't matter as long as we're going towards the new policy or the old policy. If you're going beyond that, we're going to clip it, so it doesn't matter. So basically, you can take as many or as big steps as you want, and this hard limit is just going to stop you from going too far, right? You don't have to worry about making sure you're within the trust region. That's kind of implicit, right? So that's how PPO can sometimes perform better. Okay, so let's finally now have a look at an implementation of PPO. As I said, we're going to train PPO using the ProcGen environment. So the ProcGen environment suite, as I mentioned at the end of the last video, is a procedurally generated environment by OpenAI. Basically, it's a number of different environments where they have theoretically infinite number or variations of levels. So an infinite number of levels playing the same game though. The idea is that you can vary the level layout, the colors, the backgrounds, the textures, and it was developed to try and help explore generalization of reinforcement learning. The idea that previously we were taking our agent, training it in an environment or a set of environments, and also testing it in the same set. But what we're trying to do with ProcGen is train it in a subset of the environments and test it in a different set to actually see if our agent has learned to play the game or it's just overfit, which is pretty common with reinforcement learning. So you'll need to install ProcGen if you haven't already. As I said, we're going to be using a deep residual convolutional neural network, which we'll see in a moment. So we're going to be using the coin run environment, which is this one here. You can't really see. We'll see it in the game in a second. So to actually use our ProcGen environment, it's pretty similar to the gym environments. We're going to be using coin run, and we're going to train with 20 levels. We're going to train with the first 20 levels, and we're going to be using the easy distribution mode. So easy basically means that the level layout will change between each level, but the colors and textures will remain the same. And that's just to help us train a bit quicker in this demo. Another difference is that we're going to be using many environments in parallel during the rollout procedure. Previously, we only used one. So we do a single rollout in our environment to collect data to train off of. But now what is very common is to use many, many different environments at the same time. So it's the same policy, but basically performing the rollout in a batched way. So ProcGen is optimized to perform basically rollouts or simulations of the game with a large number of environments. So we're going to be using 64. We're going to be playing the game 64 times in parallel, so at the same time, to collect as much data as we can to then train with. So going back to that loop that we saw between the rollouts and the training, but we don't just want to do it in one environment. We're going to do it in 64 to maximize the amount of data we can. Right? You can increase that if you want, but your computer may struggle. So we're going to be using the Impala architecture from this paper, Importance Weighted Actor Learning Architectures. This is basically just a simple, deep residual convolutional neural network. It's not too deep. It's, I'm not sure. I think it's like 16 layers deep. So it's still smaller than ResNet 18 or something like that. Again, for reasons we've discussed with reinforcement learning, it can be difficult to actually use large neural networks. But as we develop these algorithms, you can see the networks we can use to train with are more and more complicated. So it's basically just a CNN with some convolution residual convolutional blocks here. I won't go over that in too much detail. The actor critic part is very similar to what we saw at the end of the previous video. So I'm going to construct a data buffer as well. This is the same one we used in deep Q learning, but this data buffer will be completely refilled every time we do our rollouts. So we're not going to be bleeding data over between the different rollouts. So we'll train with a set of data and then we'll completely refill this buffer every time so we get fresh data, unlike with our Q learning where we can use some of the old data. Okay. So we have some helper functions. The first one here just converts the NumPy array that we get as the image for our ProcGen environment, converts that into a tensor in the right order, channels height width, and divides by 256 to just get it between 0 and 1, and convert it to, and this function here just does the opposite. These two functions here will do our testing. So test agent, similar to what we've seen before, and run tests will just either do testing on a number of training or test levels. So we're either going to train on test on the training levels or test on the testing levels. So I'm going to use the first 20 for training and then the next 20 testing. That's all this is doing, and just constructing a gym, ProcGen gym environment for each of those. Okay, so I've got a bunch of descriptions in here again for PPO and the generalized advantage estimate as well. Feel free to read it through it if you'd like, but I've already covered this. So let's have a look at actually how this is implemented. So instead of using the ratio here, what we do is we use the log probabilities and then we convert that into probabilities. So you can see here we get the new log probabilities, or the new probabilities of our new policy. And instead of doing the ratio, we subtract one from the other, right? Because we're using logs now. So the log of the ratio is the difference of the logs. So the difference of the logs gives us our ratio, and then we e to the power of that gets us back to the ratio of just the probabilities, not the log probabilities. So that's just a quick way of calculating that ratio. Now that we're dealing with log probabilities, I won't go into why we're using log probabilities. Hopefully you guys already know. The surrogate, or SUR1, is the first term in that objective that we have for PPO. So that's just the ratio multiplied by the advantage, as we've seen before. And the second one is the clamped one now. So we're using torch.clamp to clamp the ratio between one take, the clip parameter, and one plus the clip parameter. We're using, as I said, I think 0.2 for the clip parameter, or epsilon there. So that's just clipping it, multiplying it by the advantages, and then we're taking the min of those and then returning the mean over the batch, right? So we're doing batch gradient descent here. So we get the mean over the batch, right? So as I said, if we're selecting the clipped one and it is clipped, so if the actual ratio is between this range, we won't clip, and we'll just, and these two terms are actually the same if the ratio is between that range. But again, if the ratio is outside of that clipped range and we're choosing the clipped one, then the derivative is 0. We will not backpropagate gradients and will not update it. That stops us from pushing the probability too far or too high, because we're going to do multiple steps of gradient descent here. I didn't mention this in the slideshows, but I talked about how we can do that trust region policy optimization or trust region update with our value function as well as our policy. And so this is what we're doing here. We're calculating the critic's loss, but using the clipped critic loss, which is basically a trust region approximation for the value function. So similar to how PPO does an approximation of TRPO with the trust region. It's not in the paper. I think it might be in a later paper, but I'm using it here because it works nicely, but it's the same idea. We define the two objectives or the two terms. So here's just the mean squared error, same as usual. And then we construct this clipped objective where we take the old value and we add a bit of the difference between the new value and the old value. And this sort of constructed value we calculate the mean squared error, and then we select the max between the two because we're trying to minimize this. To clarify a little bit, so again, this is basically just a similar idea where we have a trust region we'd like to stay between. So if we imagine we have our objective or our target over here for our value, again, we don't trust it that much because our approximation is noisy. In any case, that's our target. Let's say our old value function or our old value is here, right? And our new value is over here. Well, what this constructed value does is basically take the difference between the two, this one being the new, the other one being the old, and it clips that difference to be within sort of some range, and that kind of defines our trust region either side, right? So it takes this difference, clips that difference, and adds it onto the old one, and so we get this constructed value. And then we calculate the error between the actual new one and the objective and this old one. So if this is the new one and this is our clipped one here, we find the mean square error between this clipped one and the objective and the new one and the objective, and we take the one that is larger. So our new one here is larger, and so we're going to update that to make it closer to the new one. But hopefully you can see that if the new one was actually over here, right, we've passed our trust region, we've passed our old value, then this loss here is going to be smaller than, say, this one here. And we're going to check or select the clipped objective, and we're not going to update our value function. So it's the same idea where if the value function has gotten worse compared to the old value, we can push it really far. But if it's better than the old one, given some amount, then we're not going to update it anymore because we don't trust the target of our value function that much. So we're only going to update it if it's only a little bit better than the value, not a lot, because we don't trust the actual target. Hopefully that makes sense. Okay, so again, another explanation of the generalized advantage estimate. You can go through that again, similar stuff to what I've already said. So calculating the actual generalized advantage estimate, it's similar to what we've seen before with the temporal difference learning for calculating the value function, where we start at the end and we go backwards and sort of decay the reward backwards using the value function again as the approximation of the next state's returns. This delta here, that is that advantage calculation for the current time step. And then you can see that the GAE is basically the decaying sum of those delta values going backwards in time. Note here in implementation detail is that we use these masks. These masks signal the end of a game with the ProcGen environments. As soon as a game ends, we start a new one straight away, and we get a mask value of, or we get a signal, a done signal of 1, I think, signifying the end. And so the mask is just the inverse of that, so it's a 0. And we're using that so that when we propagate those advantages, in this case, backwards, we don't bleed over to the previous game. So we multiply it by 0, it gets basically cut off, and so we can't propagate it back any further. And so that's how we can, within a single rollout, have multiple games played back to back, and then just take that whole thing and correctly calculate the advantage from that by using those masks. So this function actually calculates the advantage, or the approximation of the advantage, and using that approximation of the advantage, we actually get an approximation of the returns, which are then used for training the value function. And we do that by just saying that, well, this approximation of the advantage, we can treat that as the real advantage, and then the returns is just the advantage plus the value function, right? So if the advantage is the returns subtract the value, if we move the value to the other side and say the advantage plus the value is equal to the returns, that's our objective for the value function. Again, the advantage is basically the error of our value function. So to return to get the actual returns for the value function. We're just adding on the value to the advantage to approximate. So we got a sort of 2-in-1 there. So our update loop, this is basically just performing several epochs over our data set. So again, we have our data buffer from our a data batch from our data buffer. We do a forward pass of our model. We calculate our losses. We combine them together and perform gradient descent. And then we get the next batch and the next batch. And as I said, we're performing multiple epochs over that. And we're performing 3 epochs in our case here. There's one thing I wanted to mention as well. Here, I didn't talk about this entropy penalty. Basically, this is to ensure that the probability distribution of our agent is never 0 for some of the actions. So the entropy measures the randomness of our distribution. So if the distribution is flat, that means the actions we sample from it are really random. That's a high entropy. But as we train, what can happen with policy gradient methods is that one action really sticks out, and we can quite quickly converge to having a softmax value of 1 for one action and then 0 for everything else, which limits the sort of exploration our agent can do. Again, for policy gradient methods, the exploration comes from the random sampling. If the distribution is not random, then we can't sample any other action. The entropy penalty just keeps the entropy of that distribution above 0. Basically tries to keep the distribution a bit random so we can sample some actions. And that can sometimes, this scale factor for this loss can sometimes be annealed over time. So you can try and force it to have high randomness at the start and slowly converge off so we don't have randomness in the end. Okay. The actual objective for PPO, again, assumes some scales for the losses here. I'm not scaling the critic loss down, though sometimes it is scaled down maybe by 0.5. Again, because we've got the actor critic networks share the same parameters. So it's the same neural network producing both the actor and the critic. So sometimes you might want to scale that to balance it out correctly. Not much of an issue if they are different networks though. Okay, so defining the hyperparameters, as I've already mentioned, reinforcement learning has a lot of hyperparameters. The hyperparameters here I've taken from the ProcGen paper for their PPO hyperparameters. You can see learning rate 5e-4. We're doing 256 steps per rollout. So our rollout step, we're doing 256 max steps. As I said, that can be multiple games back to back. And we're also doing 64 of those in parallel. So for a single thread, or a single instance, we could do multiple games, along that 256 steps. But we're also doing 64 of them in parallel. 3 epochs, gamma tau, clip parameter, we've already talked about. And we're going to train for a max of 10 million frames. So again, this is the parameter saying how many interactions with the environment are we going to allow our agent to have so that it can actually learn the game. And we want this to be as small as possible. We want our agent to learn how to act in the environment with the smallest number of interactions with the environment. And we've got some loggers here, and we initialize our replay buffer, initialize our model and our optimizer. Again, I've got some more of a description of what we're doing here if you're interested, but the actual rollout loop is similar to before, or similar to what we've seen before. We're doing our rollouts. We're collecting the value state actions rewards and the masks as well. ProcGen for coin run gives us, I think, positive 10 reward when we get the coin at the end, which we'll see. But I'm just binarizing that, so it's just 1, not 10. This also should work with any of the other ProcGen environments. Again, I binarize the reward, so we either get -1, it's not really binarized. I simplify the reward, so it's either -1, 1, or 0. So if the reward is negative, you get -1. If the reward is positive, you get 1, just to simplify things. So we do our rollouts, we collect our data, put into our data buffer. Another thing here as well, another implementation detail, it is common to normalize your advantages. This just makes sure that as you train and you're sort of converging and your agent isn't doing that much better than average when we calculate the advantage, by normalizing it and make sure that the sort of average magnitude of our advantage stays constant. So even as, say, our agent is struggling to improve, the expected value of our value function isn't that much different to the calculated returns. If there's even just a little difference, by normalizing, we can sort of increase the effect of that little difference. So normalizing it over the entire data set that we've collected for this rollout or set of rollouts can actually help improve performance. And in practice, from my experience, it does help quite a lot. So we're just normalizing it, subtracting the mean, dividing by the standard deviation there. And then, of course, we do our training steps. Every 10 rollouts we do our testing the training and testing environments. So I've already gone ahead and done this. It takes a little while. It takes about an hour to train. You can speed it up. But at the end of that, about 10 million iterations, you can see the performance for our training and testing. So you can see we've roundabout converged to perfect accuracy for our training environments. So here, this is the average score across those 20 environments. So you get 10 for getting the coin. So across the 20, on average, we're getting 10, means we're successfully getting the coin in every single environment for our training set. But you can see for our testing set, that's not the case. I'm not sure, maybe average of 7.5. So around 7 or 8, 70 or 80% of the time, we're getting the coin. You can see already that issue with generalization and reinforcement learning. You can play around with this code and explore that some more if you want. But again, that's why environments like ProcGen were introduced. Again, this is the easy set where we have no color, background, texture, variation. And you can see our agent is already sort of overfitting without generalizing. But finally here, this last little bit of code will run the test agent function again with the log states flag is true, and that will just return the states and values during training. So we can save a little GIF and look at the actual value function over time of our agent performing. So we can see our value function is sort of increasing over time. Again, we've divided by 10. That's why it's not 10 here for our rewards. So it looks like it has gotten the reward. And if we look at the GIF here, you can see our agent, a little coin there. So this is the actual frames that our agent is getting. And you can see our enemies there. I think the little saw blades, you can't see at this resolution, but yeah. So maybe we can play around, try a different level. Like I said, as many levels as you want. You can see it was a bit conservative there at the start, and then the value function is shot up. So maybe it's seen the coin. Maybe it's worked out that it thinks it can get the coin. Okay, so there you go. So it's a bit pessimistic, and then, oh, seeing the coin. And I think that's when that value function is shot up there. Again, interesting. All right. So feel free to play around with this. Try some of the other ProcGen environments. You can delve into the code, or if you'd like, read those descriptions. Try the hard environments, and you can even potentially run some of the experiments they run in ProcGen, seeing how many environments or training does it take before the actual agent starts to generalize. And in essence, you need to have as many environments as there are diversity in the game. So every sort of way the games can vary, you need to have experienced that variation enough so that the agent can learn to deal with the variation. So for games where there's a lot of variation between levels potentially, you need to train with more so that your agent learns to handle that variation. But in any case, that's the end of this video. If you have any questions or suggestions for future videos like this, let me know, and I'll catch you in the next one.